Hello, this is Bio 125 Nutrition, and here we are talking about metabolism. Don't be scared now, don't be scared. I'm here to walk you through it, and we're going to get through it together. Little funny cartoon to start things off for you. How many grams of fat is that sneaker of yours I chewed up? Okay, so this chapter is not included in your textbook. There is a possibility that it's on the online version of your textbook, but no matter if you have the textbook or not, all you need is what I'm going to go through with you here in this video and in the PowerPoint. So you have everything you need. Now, why include a chapter on metabolism? Well, because if we're going to talk about nutrition, we have to. We spent a chapter talking about digestion and absorption, didn't we? So it's only logical that we talk about metabolism, right? When we talk about our nutrients, they get digested, then they get absorbed, and then they get metabolized, oftentimes metabolized for energy. So it's just a logical thing. We have talked a little bit about it here and there, but this topic definitely deserves its own chapter. Now, metabolism itself can be quite complex. The good news is we are not going to get into the detailed every chemical reaction, every enzyme, every coenzyme, la-da-da. We're not going to get into all of that. This probably will be a little challenging for some because any way you slice it, we have to talk about some of the chemical processes, but we're going to be going over it in a very simplistic way. So I believe this is something that you can handle, and we're not going to be afraid of the science. We're not going to skimp on the science, folks, right? I've really worked hard to break the information down into small, understandable pieces. So when you feel the urge coming on to be intimidated, reset yourself. Think, I can do this. And just listen, study, and hopefully you'll be able to get the basics. I think you will be. Okay. So here's our outline. We'll talk about some definitions, and then we're going to get into how our body metabolizes carbs, how it metabolizes lipids, and how it metabolizes protein. And then we'll end with some other topics. So here we go. We're going to jump right in. Okay. Metabolism, everyone's probably heard that word. When we talk about the biological definition, we talk about the definition in our body, this is it. The sum of all the chemical reactions. That's it. We tend to think of metabolism as it relates to the metabolism of nutrients. So we tend to think of, oh, you have a high metabolism, you have a slow metabolism, meaning you metabolize nutrients quickly or slowly. But it's not just the chemical reactions involved with digestion. Metabolism refers to all the chemical reactions. Digestion, yes, but everything else happening in the body. All. Now, basically, and we actually can simplify it to a large extent this way, any chemical reaction, even though it may be a combination of some, if we look at one specific chemical reaction, either it is a catabolic reaction or it is an anabolic reaction. Anything that has to do with catabolism or catabolic, it means that it's a chemical reaction that is breaking down something. You're breaking down muscle after a heavy workout. You're breaking down nutrients that you bring in when you eat. Versus anything that is anabolic or is defined as anabolism. This is a building or a synthesis. You're forming new. So formation of new proteins, protein synthesis, that's an anabolic reaction. Formation of new muscle tissue, that's an anabolic reaction. As a matter of fact, You think about anabolic steroids. You know, some weightlifters may take this. Hopefully not, but some probably do. I know some do, really. But an anabolic steroid is a steroid that's meant to build muscle. So we're building, and that's anabolism. So starting off quite simple here. So in that way, if metabolism is the sum of all the chemical reactions, and a chemical reaction is either anabolic, it's building or forming something, or the chemical reaction is catabolic, that it's breaking something down, then metabolism is the sum of all the anabolic plus all the catabolic reactions. There we go. Okay. Now there's one specific, I'm going to change this to be more specific. There is one series of chemical reactions, it's not just one. There is one series of chemical reactions that is really important to nutrition. And that is a series of chemical reactions we call cellular respiration. Cellular respiration, really, really important. Cellular respiration. Star, circle, have a party around. Cellular respiration. Cellular respiration is the chemical reactions that convert glucose into the usable energy source, ATP. Now, actually, it's catabolic, but the formation of ATP itself is anabolic. So it's a series of chemical reactions, including some catabolic and some anabolic. You don't have to know that for this part. Just be able to define cellular respiration, the process of converting glucose down into usable energy. So here's the important part, usable energy. Wait a minute, we know that carbs, glucose, sugar, we know that carbs, our cells use carbs for energy. Well, as it turns out, our cells cannot use that glucose directly, right? That glucose is just not in a usable chemical form. So while our cells love glucose for fuel, we love glucose, our cells, gives it energy, your cells have to convert the glucose into something that's usable. And this happens every day, all day. Your cells are converting glucose into ATP, converting glucose into ATP, because ATP is the usable energy source. And these series of chemical reactions together collectively is called cellular respiration. Right? So we know that glucose is a good energy source, but the glucose as it is not in a usable form. The glucose as it is not in a usable form. Therefore, we have to convert that glucose into ATP. And this chemical process, the series of chemical reactions, is called cellular respiration. If you're interested, ATP stands for adenosine triphosphate. You don't have to know that specific long name, just know ATP. ATP is the immediate fuel source, everything. If our cells are using energy, they've converted glucose into ATP. So ATP is literally the fuel. It fuels everything that our cells do. And this is a bit dramatic, I admit, but for ease of understanding, I mean, this is how important ATP is. We have to convert glucose into ATP because the ATP is the usable energy source. Usable. Without that usable energy source, our cells would die, right? I mean, it takes a lot to get there, let's be honest, but I'm just making a point. That's how important ATP is. So we're going to put it all together. We ingest food, carbs and fat particularly. You know, the food that we ingest, carbs and fat, not so much protein, but carbs and fat, it gives energy to our body. But the carbs and fat themselves are not in a usable form. So we bring in the nutrients, we digest them, we absorb them, and then your cells have to convert that glucose into ATP, the usable energy source. If I keep saying it, hopefully it will sink in. All right, now before we talk about the specifics of what we're going to talk about, we have to discuss and define a couple more things. We have to talk about enzymes and coenzymes. Now that we know that your cells have to convert glucose into this usable energy form, ATP, now that we know that, we have to discuss a couple things that are involved in that process. One thing is enzymes, and one thing is coenzymes. We need these, not just for cellular respiration chemical reactions, but for really all chemical reactions. Really for all chemical reactions. So make sure you can define these. An enzyme is something that speeds up a chemical reaction. The fancy word for that is catalyze. An enzyme catalyzes or speeds up a chemical reaction. So really, technically, we don't need the enzyme to do the chemical reaction. If we're talking about chemical digestion, the enzyme itself isn't necessarily doing the chemical breakdown. It speeds it up. And all the chemical reactions in our body, all of them, utilize enzymes. They speed up chemical reactions. How do they do it? You can see that I don't have a star beside this, so you don't need to know the specifics of how. But if you're interested, simple graph here. If we look at this level, putting it in blue, right? This level in blue, without, oh, hold on. I'm sorry, I'm ahead of myself here. I'm so excited about enzymes, I'm ahead of myself. Let's look up top here. This is the amount of energy needed without an enzyme. So if you don't have an enzyme, it takes this much energy. But if I have an enzyme present with an enzyme, it only takes this much energy. If it takes less energy to carry out the chemical reaction, well then, wouldn't it happen faster? And the answer is yes. So what this graph tells us is that enzymes work by lowering the activation energy. They lower the amount of energy needed for a chemical reaction to be performed. But keep it simple. What you need to know is enzymes are substances that catalyze or speed up chemical reactions. Would chemical reactions still occur without them? Technically, yes. Technically, chemical reactions would still occur without enzymes, but the chemical reactions would occur so slowly that your body function would be altered significantly, right? Seriously, without enzymes to speed things up, the chemical reactions wouldn't be able to keep up with the body's need. So you would die. Okay, when we talk about the enzyme structure, we're not going to get that specific. I'm just showing you some pictures, okay? In these little pictures, the enzyme is purple. The enzyme is what is going to attach to something and help to speed up the chemical reaction. What I want to point out is, I think it's on the next one, yeah. What I want to point out is enzymes display specificity. And that means that each enzyme can only work on a specific substrate. Substrate is the fancy word for whatever the enzyme is helping. On the left here, let's say that this enzyme is amylase. Well, amylase can only work on starch. So it literally has a lock and key or puzzle piece shape where it is only starch that can fit into that enzyme. The other, let's say that this is fat, the green thing. Fat's not going to fit, right? So each enzyme is specific to a substrate. The enzyme amylase can only work on starch. The enzyme protease can only work on protein. The enzyme lipase can only work on fat. So they are specific. The other thing that I want to point out about the structure and how enzymes work, enzymes leave the chemical reaction unchanged. And what that means is the enzymes can be used over and over again. So look, enzyme binds to the substrate. Then enzyme helps to speed up chemical reactions. And then after chemical reaction is done, the enzyme leaves unchanged, and it can continue to go to speed up more chemical reactions. So it's very efficient. Our body likes that. It's very good of our body. We can reuse them. Now, sometimes an enzyme needs an additional piece called a coenzyme. I'm going to use the word helper. So remember, the purple thing is the enzyme. Well, sometimes there is a coenzyme. Sometimes there's a little boop. Sometimes there's a little added structure, and that's a coenzyme. So basically they help. Not every time do we need a coenzyme, but sometimes we do. So a coenzyme is a helper. Sometimes they're attached to the enzymes and they help. We will be discussing those coenzymes later. We're going to see the specific chemicals NAD plus and FAD. Don't get too caught up in what those letters mean. They are just examples of coenzymes. They are helpers. And I use the example of them being a backpack. Because what they do is they help carry stuff through the chemical reaction. Right? There's some things that can't bind to the enzyme, but they can bind to the coenzyme. So they basically help carry stuff. They help by acting like a backpack. All right. I'm going to end this first part because the second part is going to be quite a mouthful. So I want you to be able to digest, pun intended, I want you to be able to digest this first part, and then we'll come back for part 2 to get into the actual specifics of cellular respiration.